Hello everyone. In this video we are going to talk about the set of linear equations and solving them to find the unknowns. Now you might say, well, I assume everybody knows if I give you a set of equations like this, a times x equals b, where x is a vector and b is the right-hand side known values, and a, we call it the coefficient matrix with all known numbers. Well, everybody knows to do x equals a inverse times b, right? That's not a big deal. So what are you going to talk about, which is a little bit different or beyond what we have seen? Well, we're going to talk about it. So the thing is, not always when you get a set of equations like this, the number of unknowns and the number of equations are the same. If they are the same, it's basically a square set of equations. The equations and the unknowns are the same, but that's not always the case. So sometimes you might have this to be like an m by 1, so you have m unknowns, right? This is an n by m, and this b is an n by 1. Okay, so what does it mean? It means that basically you have n equations and m unknowns. Okay, so here you have m unknowns and n equations. And not necessarily always this m and n are equal. Sometimes m is bigger than n, sometimes n is bigger than m. Now what? Now can you find a solution? Okay, so we call them over and under constraint equations. So we're going to talk about those, and then we go back to the case that m and n are equal, so the set is a square. Talk about under what condition you can find a solution. Depends on whether the right-hand side vector b is 0 or not, so the equations are homogeneous or not. And then we're going to talk about something probably new to many of you called the condition number, which basically tells me about the accuracy of the solution. Okay, so let's consider different scenarios here, right? First, let's assume that the number of equations is bigger than unknowns. This set of equation, we call them over constraint. So you have more equations than unknowns. Like what? Like one of the famous examples that you know, and we talked about it in one of our previous videos, are curve fitting problems, right? So let's say you have done the Hooke's experiment. You basically hang a spring from a fixed location, and you suspended a bunch of weight from it, you measured the deflections, and then now you are plotting the force in the spring, which is equal to the weight of those masses, versus the deflection of the spring, F versus delta. Okay, and here you got a bunch of data points. And now your goal is to pass what we call the line of the best fit, like that, through these points. Correct? So you know you can never get the line to pass through all of these points. Why? Because the equation of this line is something like y equals like cx plus d, right? And here, let's say you have 6 points, correct? So here you have 6 points, which corresponds to 6 equations, and then you only have 2 unknowns. So clearly, you cannot pass this line through each and every one of those points, because all you can vary are these 2 parameters, 2 unknowns, and you have to fit 6 equations. So you have to have something like, hey, could you plug in this point x1 and say y1 is equal to cx1 plus d1? So yes, maybe. Now, can I add one more point and you make sure this point also passes through the line, or line passes through this, or that is on the line? Well, still I'm okay. But now that you add the third and the fourth and the fifth point, now it is not going to be possible, right? So it is not going to be possible to pass the line through all of these points. And what you will do is, at best, try to minimize the distance between this line and the points. Okay? So you have this. Clearly, as I said, if you look, you have a set of what? Linear equations. If you want, you can write this in the matrix format. So you can write it as the coefficient matrix with, as you can see, C and 1, correct? Or sorry, x1 and 1. Then x2 and 1. Or if you want to write it the other way around, you can write it as 1 and x1, 1 and x2, 1 and x3, 1 and x4, 1 and x5, 1 and x6. This whole thing times D and C is equal to y1 and y2 all the way to y6. Correct? So you clearly see that now you have two unknowns. This is your matrix A, that is your right-hand side vector B, and this is your unknown vector X. Clearly you cannot solve, as I said, okay? There is no solution whatsoever. You can never find an accurate, exact solution. So what you do instead, this is what you do. You try to bring y1 to this side and say, hey, this minus y1 is equal to some parameter and call it e1. Since you can never get the point to be on the line, unless exceptional cases, then you bring this constant y1 to the right side, say, hey, ideally it should be 0, but since I cannot make it exactly to be on the line, I say this is equal to what we call a residual term, an error term, and I call it what? E1. Then do a similar thing here, bring this guy here, call it what? E2, and then repeat that for all other equations. And now your goal is to make these errors as small as possible. And the matter of fact is, you might make one of them very small, the other one go big, and if the signs are considered, then big positive and big negative signs could cancel each other. So what you do, instead of just, you cannot individually minimize them, what you need is one metric, one measure. And what you do is you say, what I'll try to do is this: e1 squared plus e2 squared plus e3 squared all the way to e6 squared. I'm trying to minimize some of these squared errors. And I'll find my C and D, or D and C, doesn't matter, to be what? To be values that minimize this function. Because clearly you see this function does depend on, each one of these e's depend on C and D. So this sum of square roots clearly does depend on C and D. You say argument of the minimum of this function. Okay, and then you can do what we call the least squares curve fitting, right? Where the solution the optimum solution, which gives you the minimum to the sum squared, you can see that this x least squared solution is going to be what? You cannot clearly invert this A and multiply B because this A is not a square matrix. So what you do instead, you multiply a version of A, which is like a generalized inverse. We call it the pseudo-inverse. Okay, times B. We call it Penrose-Moore pseudo-inverse. Okay, and what is the pseudo-inverse? It is actually A transpose times A inverse times A transpose. Okay, this guy, you know, if you multiply it by A, right? If you multiply this pseudo inverse by A, then this guy and this one are inverse of each other, plus A transpose A is a square matrix, so you can invert it, and you know, inverse of any square matrix time itself is I, so you clearly see that a pseudo-inverse times A is I. That's why you call it what? Pseudo-inverse. So it acts like an inverse. When you multiply it from the left side, you get the identity matrix. But we call it pseudo-inverse because A is not a square, so it's kind of similar to an inverse, but not the real inverse. So in this case, as I said, the least square solution is basically pseudo-inverse of A times B, okay? So just keep in mind, again, if your set of equations is over-constrained, you have more equations than unknowns, you can never get a unique, accurate solution. All you can get is to minimize something like this, a cost function, which is in terms of the errors, which is in terms of, let's say in this case, these vertical distances of these points from the line. You're trying to minimize a cost function of some type of error by setting basically those parameters to minimize the function, as I said. Okay, so over constraint system, no unique solution. The best you can do is minimize the error. Now, what about the other side where you have less equations than unknowns? By the way, I mentioned and I talked about this least squares. So if you go to my channel and go to playlist and then go under math, you can see there is a video where I talked about the, let me find it for you, the least squares here, linear least squares curve fitting. Okay, so here I talked a little bit more about that topic. Curve fitting is in general an over-constrained system of equations. So if you want, you can refer back to that. Now, as I said, there is the opposite case of it. Here, m is bigger than n. You have more unknowns than equations. So your set of equation is called under constraint. Now what? Now, can you get anything? Okay, more unknowns than equations. So let's say here you have something like, for example, 2x plus y minus z equals 1, and then negative x and plus 3y, and then plus z is equal to 4. Okay, so here you have two equations, three unknowns. And as I said, you can rewrite this into the matrix format by saying 2, 1, negative 1, negative 1, 3, and 1. This guy times x, y, and z is equal to 1 and 4. Okay, and clearly here, if we call this A, this is unknown vector, whatever you want to call it, and this is B. Let me not call it X because X I have something else. Maybe I call it unknown vector Q. So of course I cannot invert A times B, and first we have to talk a little bit about it before getting into math details and linear algebra details is how can you solve this? Well, here you have more unknowns than more parameters to tune than the equations to satisfy. So you can clearly say that, well, I can pick z because z is more than what I need. Ideally, to satisfy two equations, I only need two unknowns. So one extra one here is basically redundant. So maybe I pick my z and set it to 0. Now I have a square system, correct? Because I can write it as 2x plus y is 1, negative x plus 3y is 4. And let's say here, if I solve for it, so I set z to be equal to 0. And so now what can I write? Well, if I go ahead and eliminate x between these, so I multiply the bottom one by a 2, add them together, you're going to get 7y, and 7y is going to be equal to 9. So y is going to be 9 over 7. And if I plug it back into any of these equations, x is going to be 3 times y minus 4, so it's going to be 27 minus 28, 1. This is going to be 1 over 7 if I'm not mistaken, because that's 27 minus should be, I assume, negative 1, right? So 3 times that, that's 27, plus 1, that's 28. 28 over 7 is 4, okay? So that should be your solution, and here you can check it. Negative 2 over 7, 9 over 7, that's 7 over 7 is 1. So this is one solution, right? I just set z to be equal to 0. Then I might go ahead and change z and say, no, well, who said I want z of 0? I want z to be equal to 1. What if I choose z to be equal to 1? If I do that, now your equation, the top one is going to be basically 2x plus y. This is 1 here. Goes to the other side, becomes 2. Correct? And here it becomes negative x plus 3y equals 3. Right? So now these are your equations. Again, you multiply the bottom one by a 2, and you will get 8, 7, so y is going to be 8 over 7, and if you plug it down in the bottom, it's going to be 24 minus 21, 3. It should be 3 over 7. Okay, and then you can plug in other z values and get other values of x and y and so on. So what you can see here is for any solution, for any number of z I put in, or at least for most of them, I can say, I can always get the solution here. So the answer is, how many solutions would I get overall? Infinitely many. Okay, why? Because my system is what? Under constraint. So I have no limitations of choosing one of my, at least, or several of my variables, as many as I have redundant, which is m minus n variables. I can choose as many as those free, and then I can pick the rest of them. So clearly the solution here is what? The solution is infinitely many solutions. Okay, that's what you have. Infinitely many solutions is what you get. For the top one, the solution was what? For this case, the solution was no solution. Okay, at best you can get some minimal error function, but you can never get accurate, no accurate solution. So that solution you have is what we call at least a square solution. There is no accurate solution. You can never pass those. Let's say that line through those many points. You can never satisfy all those equations, right? So that's what you can see here. infinitely many solutions. And now the last case is, what if m is equal to n? Then here you have a square system, and here we have to discuss what happens, because we always know, yeah, there is a unique solution. Not necessarily. We have to talk about it. But before I jump into this square system, since I mentioned an example for over-constrained system curve fitting problems, what about under-constrained? Is there any application anywhere that you know in engineering, in math, that the system you have to deal with is under-constrained? Yes. In general, you can see that the eigenvalue problems are under-constrained problems. Okay, I mean, the eigenvalue themselves, no, there is an equation you will get in general an nth order polynomial, and the roots of that are eigenvalues. But it's when you go and determine the eigenvectors, what you will get with the eigenvectors are just a ratio. Okay, so for example, if I have a matrix like this, 1, 2, 4, and 6, when I get the eigenvalues, right, it gives me two eigenvalues. And when I get the corresponding eigenvectors, v1 and v2, then all I have is actually two ratios and not just these two vectors. Let me show you that. 1, 2, 4, 6. So here I say v and d is equal to eig of, and then it was again 1, 2, 4, 6. And you see that the numbers are negative 20.27 and 727. Okay, and the corresponding eigenvectors are these guys. So negative 0.83 and 54. 84 and 54. And here I'm using two decimals, of course. And here is the other one is 31 and 95. 31 and 95 both negative. Okay, now the matter of fact is, not only these v1 and v2 are eigenvectors, which means if you multiply this matrix, let me call it A, if you multiply A by v1, the result is going to be lambda 1 v1. And if you multiply A by v2, the result is lambda 2 v2. Not only that, any multiple of v1 and v2 fits this equation. And you can clearly see that if instead of v1 I do a times v1, or not a, let's say c times v1, where c is just a constant, here you can get c times v1, and here you can get c times v1, and you still have both sides of the equations to be equal. Okay, so what you really will get when you are solving for eigenvectors is basically you get here two equations when you are trying to solve for v1, but the two equations are the same. They are not linearly independent from each other. So what you really have is two parameters to choose and one equation, not two equations. Let me write it for you very fast. So you know, once I determine my lambdas, let's say I determine this first lambda, the way to go about v1 is, you say from here, you clearly can see I can write it as a minus lambda 1I times v1 is vector 0, correct? And if I write it, my a is 1, 2, 4, and 6. This minus lambda 1I means on the diagonal just subtract lambda 1, and lambda 1 is negative, so you have to add that 0.27 on the diagonals. So this guy times v1, which has, let's say, two components, x and y, this is equal to 0 and 0. Okay, so here you will get two equations, correct? One of them is like, for example, 1.27x plus 2y is 0, and the other one is like 4x and then plus 6.27y is 0. And guess what? Here, it seems like you have two equations. It's a homogeneous set of equations with two unknowns. But the matter of fact is, whatever number that you multiply to get 1.27 to 4, you have to multiply that same number on 2 by 2 to get 6.27. So basically, if you multiply this whole equation by one single number, which is 4 divided by 1.27, you're going to get the bottom equation. So they are linearly depending on each other. So basically, either I have the top equation or I have the bottom equation. Let's say I only have the top equation, okay, which is 1.27x plus 2y equals 0. So now you have two unknowns and you have one equation here. So m is 2 and n is 1. So you clearly see that when I'm trying to do eigenvectors, my number of unknowns is more than my number of equations. And what they typically do is they choose one of these guys and they determine the other one. And what they typically do is they choose one of them to be 1. So let's say they choose this one to be 1 and then they determine this one, or vice versa. We call it normalization. But you clearly see when we go to eigenvectors, all that really matters is the ratio, which determines the direction of the vector. The magnitude of the vector is of no importance. So eigenvalue problems, when you go to eigenvectors, it is an underdefined problem. Okay, you clearly can see that. And of course, there are infinitely many solutions. We just choose one of them here by picking one of the x and y and calculating the other one. But the thing is, all of those infinitely many solutions here, they all share the same direction. Just their magnitudes are different, and that's what we care about in eigenvectors. Direction. Nobody cares about their magnitudes. Okay, as I said, I'm going to make a video and explicitly talk about eigenvalues and their applications in engineering. But just wanted to remind you, one of the places where you see under constraint problems. Talked about over constraint. Now, many of the times, as I said, you are going to see a square set of equations. So you have exactly as many equations as the unknowns, which is really good, right? But there are some reservations and there are some stuff we need to talk about. So when you write it as a times x equal b, and here the dimensions match, so if this guy says m is the same as n, so you can write it as n by 1, this is n by n, and this is n by 1. Okay, so everything looks good. Now what? Do you have a unique solution or not? Well, it depends on this right-hand side, whether the right-hand side is 0 or it's not 0. Okay? So let's look at several scenarios. Scenario 1 is this vector b is not completely 0. So it doesn't mean that a few of the components of this b cannot be 0. Yes, they can. But not all of them could be 0 at the same time. Okay, so the fact that I wrote here b is not equal to vector 0 means not all of the right-hand side numbers in B are 0. Some of them could still be 0, but not the whole thing. If that's the case, which we call it what? A non-homogeneous set of equations, then, so let me write this a little bit more organized. So if the set of equation is what? Non-homogeneous, which means b is not vector 0. That's one position we have to talk about it, and the other case is what if b is 0? Okay, so the set of equation, we call them homogeneous. which means B is 0. So all of the right-hand side is 0. So you're basically solving A times X equals 0. Now what happens? If it's not homogeneous, there are two scenarios. Either the coefficient matrix has 0 determinant or it doesn't have 0 determinant. So in general, the solution is X equal A inverse times B. Okay, as you know. Now, not always A inverse does exist. Sometimes it doesn't exist, and you know, for a square matrix, it doesn't exist when what? Yes, when the determinant is 0 or the matrix is not full ranked. So here, if the determinant of A is not equal to 0, so matrix is not singular, so the inverse does exist. If that's the case, then there is what? There is a unique solution, one unique solution. If no, the determinant is 0, then there is no solution. So because your set of equations are not consistent, okay, it's not possible to have such a thing. Let me show you an example of this one. So right-hand side is not 0, but the left-hand side determinant of the coefficients are 0. Like what? Let me show you a case here. My pen writes. So I have like x plus 2y equals 3, and then 3x, or let's say 2x plus 4y is equal to 5. You know, this is not possible. Why? You clearly see my coefficient matrix here is 1, 2, 2, and 4, correct? Clearly it has a determinant of 0. The right-hand side is not 0, so it is this bottom case. And is there any solution? No, because if I multiply the top one by a 2 and subtract from each other, you will get 0 is equal to 1. 2 times 3, 6, minus 5 is 1. And this is not possible. Okay, so there is absolutely no solution when the determinant is 0, but the right-hand side is not. Okay, so just keep that in mind. If the right-hand side is not all zeros, the only possible scenario for a solution is the coefficient matrix has inverse. It's not singular. Okay, that's the only scenario. Now let's talk about the case that the set of equations is homogeneous. So the coefficient matrix can have different scenarios, but the right-hand side is all zeros. So here, again, if the determinant of the coefficient matrix is 0, then there is only one solution. And that unique solution is x equals 0. So it means all of the variables, unknown variables, have to be 0. Here, not necessarily, okay? So here, not all of the x components are 0, because the right-hand side is not all 0. Now, if in this case the determinant is 0, if the determinant is also 0 and the right-hand side is all 0, then you can show that this one has infinitely many solutions. It basically can be reduced to an unconstrained, under constrained set of equations. okay, it will be converted to an under constraint set of equations, just like the previous example I mentioned for you. So let's say 2x plus y equals 0, and then 3x, or let's say 4x plus 2y is also 0, right? Clearly, again, the determinant of the coefficient matrix is 0. The right-hand side is 0. Clearly, there are infinitely many solutions, because from the bottom one, you see that y is negative 2x, and from the top one and the bottom one, both, if you simplify, you see the result is the same. So as long as this simple relation exists, you can choose any x and it gives you the corresponding y, and you can choose any number for x, so there are infinitely many solutions, okay? So you see that a linear set of equations that is square can have all sorts of answers. Unique solution of 0, unique solution non-zero, infinitely many solution, and then no solution. Okay? And that's different from over and under constraint. One of them had no solution, the other one has infinitely many solution. But other than this, there is another important thing we need to talk about in this set of linear equations, and which are square, and that is called a condition number. So what is that? So a condition number in general for a matrix, we call it kappa. So the number kappa for a matrix A is defined as well, it is a little bit mathematical. I don't want to get into too depth of mathematical definition of that, but it is basically like the maximum value that AX can take over X, where X is an arbitrary vector. This is a norm. It could be any type of norm, okay, two norm, absolute norm, whatever. There are so many norms. If you don't know them, in my videos that I'm going to publish on linear algebra, I'm going to talk about different norms, different types of norms for vectors. But what you really want is, if I change my vector x, and in the numerator I multiply it by a and take the norm of it, in the denominator I just take the norm of the x itself, and I evaluate this ratio for what? For any possible vector x, then the maximum I can get out of this ratio, we call it what? We call it the condition number of matrix A, okay? So in mathematical books, they use supremum of this, but I'm just trying to tell you simpler. It's the maximum value that this ratio can take by changing x to any arbitrary x and then seeing which one can be the max. Now, if the matrix is square, so if A is an n by n square matrix, like what we have for the sake of matrix set of equations, then you can show that this kappa of A is basically the norm of the matrix A times the norm of A inverse. Okay, so if, and here norm again could be any norm. We can use the 2 norm, we can use the Manhattan norm, we can use the infinity norm, we can use the Frobenius norm, and so on and so forth, okay? So this is one way that you can show it. In general, if matrix A is not square and it's rectangular like this, then you can show that this is equal to maximum singular value over minimum singular value. Again, what are these? I don't want to get you into too much of math. I'm going to publish soon a video, as I said, on eigenvalues, on singular values, on the norms for matrices and vectors. These are very important topics that we need to talk about. But what's the meaning of this? Forget about all the math and all the definitions and everything. What's the meaning? What's the meaning of this condition number? Well, what it does, it shows the accuracy of this solution. So when I go and solve here by A inverse times B, it is trying to tell me how sensitive the solution are to small changes. Okay, what do I mean by that? So here I'm going to show you two different sets of linear equations where I'm trying to solve for x and y, and then show you the accuracy or the sensitivity of the solutions. So my first set of equations is something like this. 2.x plus y is equal to whatever you want. Let's say -1. And the other one is like 6.1 times x, and then plus 3 times y is equal to, let's say, 4. Okay, so this is one set of equation. In the other set of equation, I write something quite similar. So 2x plus y equals -1. And then instead of that 6.1, I make it like, let's say, 8.1. Or 7.1, or whatever you want. Okay, now I'll try to look at the solution here. So what's the solution here? Clearly, if I solve for x and y, it is going to be, let me do that. So 2, 1, 6.1, and 3. 2, 1, 6.1, and 3. And then b is -1 and 4, right? And the solution is a backslash b, or a inverse times b, whatever you want. And you see the solution is 70 and -141. Yes? That's my solution. Now let's look at the solution of this one. So what is it here? So here I just changed my number to 8.1. So this is going to be 8.1, and the solution is 3 and 1/3 and -7 and 2/3. So it is 3.33 and -7.67. Okay, so you might say, well, yeah, I can see something. The numbers are getting bigger, but that's not really the major problem here. That the numbers are bigger here, that's not really the major problem. The solutions should be different because one of the coefficients is changing. The problem is here. If in this equation I change this coefficient from 6.1 to something slightly different, or any other one of these coefficients, okay, any other one of them. So if I make this 6.1 just 6.2, correct? So let's say in my application, in my engineering application, I found that one of the parameters I had was slightly different. And so I came back, I changed it slightly, and now I'm looking at the new solution. Well, what do you expect? Do you expect this new solution to be close to the previous one? That's kind of intuitive, obvious, right? Because you just change one of the parameters very slightly. You don't expect the numbers, the solutions to change like crazy from last time, right? A small change in the physical system probably means a small change in the solution to that system, right? Well, let's find out. If you make it from 6.1, 6.2, what can happen? So I do it and I get my solution, and now look, 35 and negative 71. Look at the change. This one is changed by 35 units. And this one is changed by plus 70 units. You see how huge they have changed? Now let's do the same thing here. Instead of 8.1, I make this guy 8.2 and look at the solution, right? So in this system, if I change one of my parameters slightly, what will happen to the system? So here I make it 8.2 and apply it, and I get 318, 736. And now look. You see, this guy has only changed negative 0.15, and this one is changed about 31, right? Positive 0.31. Now you might say, well, it's not fair to compare these changes against this because the numbers we started with were way bigger here compared to here. You're right. It's better to compare in terms of percentage of change, not just the magnitude. Well, 70 going to 35 means how many percentage? It is what? It is reduced in half, so that's 50% reduction. And this guy almost the same, correct? That's also a 50% change, right? What about here? Look at the change here. Is 0.15 compared to 333, which is about 22 times bigger. So this is equal to 1 over 22%, which is slightly bigger than 4%, okay? So 1 over 22, or if you want, 0.15 divided by 3.33. Yes. So this is just 4.5%. And here the change is 31 over 767. 31 over 767, which is about 40%, 4%. Now, even you see in terms of percentage, these equations on the left-hand side are changing way, way more, orders of magnitude more than the equations on the right-hand side. Why is that? Why is that the set of equations on the left, although they look quite similar to the ones on the right, are so sensitive? If you change, and it's not just this 6.1, if you change other ones, right? So instead of this 6.1, let's keep it back and change one of these other numbers to something, you still see that your system is quite sensitive. This one, any of them that you would change a little bit, you will not see as much sensitivity, just like this case. So what is it that makes the system very sensitive to small changes? That's this guy here, the condition number of the coefficient matrix, okay? So if you look at the coefficient matrix here, the coefficient matrix is 2 and 1, 6.1 and 3. And if you look at the determinant of this guy, it is a negative 0.1, which is a small number. For the other one, where it is 8.1, the determinant is negative 2.1. And we know that when we have what? A determinant of 0, then you are going to get crazy types of behaviors, right? So from a unique solution, you go to no solution or infinitely many solutions. It's not really a good idea that your square matrix is having a determinant of 0. When it's the determinant of 0, we call it what? We call it the singular matrix. Correct? So in the top case, your matrix is closer to being singular, while in the bottom case, or here the right case, it's further away from being singular. So that's the meaning of this guy, condition number. Condition number means how close your coefficient matrix is to being singular. Okay? The closer it is to being singular, the more sensitive your system is to smallest change in the parameters. Your solutions would change significantly. While where is far away from this singularity, which means determinant is not really small, then this kappa number here, which is going to be small, actually it makes the system less sensitive. And so let's take a look at the condition number. In MATLAB, there is a command called cend. And if you apply it to this matrix A, so right now your matrix A, let me change it back to that 6.1. And if I calculate the condition for A, you see the number is 512. That's a huge number. Now, if I change it to 8.1, and calculate it again, the number is only 37. So you see, the bigger the condition number is, the worse your set of equations will be, the more sensitive it is going to be. So if I want to write it somewhere for you, when k is large, your set of equations is sensitive. We say the set of equations is ill-conditioned. Your set of equations are ill-conditioned. Okay, and when k is small, we say they are well-conditioned. Well-conditioned means they are not so sensitive to a small change in parameter. Ill-conditions mean they are extremely sensitive. So remember that whenever you're trying to solve a set of equations, it's always a good idea to calculate the condition number and make sure your system of equations is not ill-conditioned, because if they are, then you change any of the parameters during your solutions a little bit. Because of any revisiting of your numbers, you're going to get significantly different solutions. And that's not a good idea. So I just wanted to tell you about this very important thing, condition number. And the way that MATLAB calculated it is exactly actually using these singular values, or by calculating the norm of matrix A times the norm of inverse of it, which norm we'll talk about it. But in MATLAB, you can always use the command svd for singular value. If you run it, it gives you all of the singular values of matrix A. So you see, this is the largest singular value, this is the smallest, and if you divide them, you see that ratio is the same as your condition number. So that's all it does. When you call the command condition, it finds the max singular value and min singular value and divide. That's all it is. Okay, and you can apply it, since it's singular value, you can even apply it for non-square matrices as well. But just wanted you to know, we'll go a lot into details of what singular values are, what is the norm, and so on. So please watch our future videos. But as you can see, solving a set of linear equations has a bunch of details, okay? Whether it's a square, over, or under constraint, there are some stuff we need to talk about. Thank you.